Okay, so one thing we came across in chapter 5 is don't know how to integrate a product when we've got two functions that's a product. In other words, it's kind of like undoing the product rule. Okay, so one way to do this is a u-substitution, and what we're going to do is going to say one. So what you're trying to say with this is that one function is the function, and then the other function is the derivative of that function. Okay, and so that's basically the substitution you're trying to do. All right, that's where we're going to undo this. So here's the first one on that worksheet that I gave you, and they suggest to do it two different ways, and this is the definite integral. So when we're done, we're going to have an answer because I got the values I can evaluate it at. So what we're going to do is we're going to ignore these bounds for a minute, and I'm going to just concentrate on this. So do you see how what's inside here is x squared plus 1? And if I take the derivative of that, that's 2x. So what I'm going to do is I'm going to say, hey, let u equal x squared plus 1. The derivative of u with respect to x is going to be 2x. And then the derivative of of 1 is 0. Now, here's the part that's I glossed over this part. We didn't really look at this idea of differentials. And momentarily what we're going to do is we're going to pretend that this is a fraction. It's not. This is a noun. This is the derivative of this function is. So, but what we can do is we can say y changes, as u changes, x changes a little bit. That's why it's almost like a related rate kind of thing. So what I'm going to do here is I'm going to pretend that dx is a fraction, or the denominator of a fraction, and then I'm going to, I don't know if it'll let me erase this. I'm going to white that out so you don't see it anymore. It's not whiting out very well. Okay, so du equals 2x dx. So what that allows me to do is I can say, well, instead of writing x squared plus 1 cubed, I can write u cubed. And instead of writing 2x dx, I can just write du because this is 2x dx is that, so I can replace that whole thing with du. So that what that brings me down to is an integral of u cubed du. Now that's very easy to find the antiderivative of. I'm just going to use the power rule. So I'm going to add 1 to the 3, and then I'm going to divide by 4. So I'm going to write it like 1/4. And I could think of it as plus c, but because I'm going to evaluate this at a point, the c is going to cancel off. So because I've been dealing with this is these bounds were in terms, remember it was 0 to 2 of whatever f of x was, dx. So what we've got is x's. These are x's, and we're dealing with u's, so we have to do this back substitution. Instead of writing f of u equals 1/4 x to the 4th, f of u equals 1/4 u to the 4th power, we're going to replace the u, back substitute the u with the x squared plus 1. So now f of x becomes 1/4 of x squared plus 1 to the 4th power. Then plus c, of course, but we know that's going to subtract off. And then when you evaluate that, now that I'm back in terms of x, I can evaluate that from 0 to 2. So if we think about this, let's see here. I'm going to drop in 2. 2 squared is 4, plus 1 is 5. 5 to the 4th power is 625 over 4. And then we're going to subtract, so that's the f of a, or f of b, minus f of a. And that's, I hope you remember, is the fundamental, one part of the fundamental theorem of calculus. So now I'm going to drop in 0 into my function. Well, 0 squared is 0, of course, plus 1 is 1. To the fourth power is 1 minus 1/4. And then 625 over 4 minus 1 over 4 is 624 over 4, which I believe is 156. So that's what that integral is equal to. So that's without doing any kind of limit change. And it's certainly acceptable to do that. In fact, the first year I taught this course, I kind of ignored the changing the limits, and kids got caught on the AP test with it. So now what I'll do is show you how to do the same thing, only instead of changing and keeping it in terms of x, we're going to change these things so we don't have to go back to x. So we've got this integral, and we did this substitution, and we found that for the antiderivative. So now what we can do, so we don't have to change it back to x, we can actually say, okay, so let's change our bounds. We're going to integrate this from 0 to 2 in terms of x. Well, what if we use u? So if I drop 2 into my u function, that's 2 squared is 4, plus 1 is 5. And then I'm going to evaluate, and then f of 0 or u of 0 is going to be 1, right? Because 0 squared is 0 plus 1 is 1. So then what we can do is what we really did is we changed our integral to this. That evaluates to this, and then we're going to apply the fundamental theorem of calculus to this. So that's going to become, we've done this math already, 5 to the 4th is 625 over 4 minus 1 over 4. And you see how that's the same math we just did? Much easier to change your bounds when you're doing a u-substitution. So here's the next example I'm going to work for you. So we've got this, looks to me like we want to go, now that's the thing I probably should do. Suppose I think, well, my f function is going to be 1 minus x squared. If I take the derivative of this, it's going to get complicated in a hurry, right? Because I've got that radical I got to worry about, I've got a chain rule I got to worry about. This is not getting more simplified, it's getting more complicated. So what this lets me know is that I chose the wrong thing for you. So instead, and I'm going to say u equals what's underneath the square root, take the derivative. Now unfortunately, do you see how I've just have an x, so this is easy, right? U equals, I can do the square root of u, but see how I have this x dx left? And what I have over here is negative 2x dx. Well, this extra negative 2 is problematic. So what I can do is I can divide both sides by negative 2, bring it over to the du, and then I can replace the x dx with a negative 1/2 du. So I'll write that, negative 1/2 du. And then, of course, I'm going to do that bound change, as I just barely did. So what's u of 1? Well, u of 1 is 0, because 1 minus 1 squared is 0, and u of 0 is 1. So I can replace this with 0 and this with 1. And notice the place, I know you want to put the 0 down here, and we're going to make it put it down there. But for now, that bound became 0, that bound became 1. So what are some things we can do to clean this up? Well, this is the negative 1/2 is a constant, and because it's a constant, I can bring it in front of the integral. So negative 1/2 times the integral from 1 to 0 of the square root of u du. And then, of course, let's fix these bounds because we want the lower one on the bottom. So I'm going to switch 0 and 1, and of course what I'm hoping you remember from before is that when we switch those bounds, those limits of integration, we have to change that sign. So that's going to become positive 1/2 from the integral from 0 to 1. And of course I'm going to change that radical to 1/2 right now. So that's what we're going to integrate. So a lot of prep work to take something that looks awful to something that's not too hard. So to integrate this, I'm going to say, remember, I'm going to take the u to the 1/2. I'm going to add 1, which is 2 over 2, which becomes u to the 3/2. Then I have to divide by 3/2, which is the same as multiplying by 2/3 times u to the 3/2. Now we can't forget about this 1/2 that's out in front of the integral. We're going to evaluate that from 0 to 1. What's nice about having 1/2 in front, those 2's will cross cancel off. So that's going to give me 1/3 times u to the 3/2. Now let's evaluate that from 0 to 1. I'm going to drop in 1. I'm going to take the square root, which is 1. I'm going to raise to the 3rd power, which is 1, times 1/3 is going to be 1/3 minus, if I drop in 0, I'm going to get 0 to whatever power is 0 times 1/3 is 0. So this 1/3 is the integral, is the area under the curve of that awful function. Sine in itself isn't too bad. Sine 2x, well, that's a little more complicated. So here's a perfect opportunity for a u substitution. And what do you think u should be? I hope you said 2x. So what's du? 2 times dx. So that means, and then of course, I don't see a 2 off by itself here. So I'm going to have to do that trick where I'm dividing du by 1/2, or dividing it by 2. And then, of course, let's change our limit so we don't have to do that back substitution. So u of pi over 4, and I'm jumping ahead of myself here. U of pi over 4 is 2 times pi over 4, which is pi over 2. And then u of 0 is 0. So I'm not seeing any change as far as having to switch those limits. Instead of sine 2x, I'm finding the sine of u, du, and of course I can't forget about the 1/2 that I had, and I'm just going to bring that in the front. So now, what's the antiderivative of sine u? I hope you said negative cosine u, and then I'm also going to have that 1/2 that I'm going to bring along for the ride. Why did I make it negative? Oh, because the negative sign, right. So then I'm going to evaluate that from 0 to pi over 2. Well, we're going to drop in pi over 2 and for u, and I hope you remember that the cosine of 90 degrees, the cosine of pi over 2 is 0. So we're going to get 0 minus negative 1/2 times the cosine of 0. Well, and I hope you remember that the cosine of 0 is 1. So 1 times 1/2 is 1/2, and a double negative makes it positive. So that is equal to 1/2. So check it out with f and int. Here's another one. There's a radical. Maybe we should let what's under u be what's under the radical. The other flag that tells me no, that's probably the correct decision, is what's the derivative of the cosine? This negative sign. So that is the wise choice. So u equals negative sine x dx, and then we've just got that extra negative kicking around. So now we can let sine x dx be replaced with negative du, and because the negative is just a constant, I can bring that out in front. And I'm going to write this as u to the 1/2. I'm going to have a du. Now the only thing I need to change now is my limits of integration. So what's u of pi over 2? Well, that's going to be the cosine of pi over 2, which is 0. And u of 0, well, the cosine of 0 is 1. So that's going to give me 1 to 0. And of course, I'm noticing that these limits are in the wrong position. I want to have the lower one on the bottom, so that means switching the signs. So that becomes 0 to 1, u to the 1/2 du. This is looking much easier already. So the antiderivative of u to the 1/2 is 2/3 u to the 3/2. We've done that enough times, so I hope I don't have to explain that. So 0 to 1, drop in 1, we're going to get 2/3. Drop in 0, we get 0. There's my integral. Here we go, another one. I'm hoping, take a look at it. Stop the video. See if you decide what you want to pick for u. And then come on back and watch what I'm doing. Okay, so I hope you said that u equals pi minus x squared. Du equals negative 2x dx, because pi is a constant. And I'm not seeing a 2, I'm not seeing a negative 2 in here. So I'm divide du by negative 2. So that'll let me replace negative 1/2 times the integral of sine u du. And then let's fix the bounds. So what's u of the square root of pi over 2? Well, I'm going to take x and square it, so that cancels out the square root. And pi minus 1/2 of pi is 1/2 of pi, so pi over 2. And then u of 0, pi minus 0 is pi. And so again, I've got bounds that are upside down, so I'm going to switch them, change that to a positive. So pi over 2 to pi of sine u du. So the antiderivative of sine u is negative cosine u, and I'm going to bring that 1/2 along for the ride. And we evaluate this from pi over 2 to pi. If I drop in pi, the cosine of pi is negative 1 times negative 1/2 is 1/2 minus negative. And if we drop in pi over 2, the cosine of pi over 2 is 0. So that whole mess becomes 0. So 1/2 is the area under that curve. So now we're going to recall some stuff from chapter 5 where you're breaking up using those integral rules. But we're going to apply the u-substitution to it. I'm seeing all of these being just f of x, and I've got f2x. So that tells me, what if we let u be 2x? Du equals 2 dx, or 2 dx, right? And then if I divide by 1/2, that'll give me 1/2 du equals dx. If we change our bounds, u of 2 is 4. U of 0 is 0. So what I'm going to integrate is 1/2 times the integral from u to 4 of f of u du. And they're telling me, if I look up here, from 0 to 4, f of x dx. Remember, the x's are dummy variables, the u's are dummy variables, so those don't matter. This is telling me that this area is negative 1/2. So this whole thing becomes 1/2 times negative 8, which is negative 4. Okay. Why don't you think, I'll try to apply that same kind of thinking here for 0 to 2. Notice that's 0 to 2, so we should be able to do something with this to be able to use that 4. So I'm hoping that you said u equals 1/2 x, du equals 1/2 dx, so 2 times du equals dx, which, and then we say if u of 2 is 1, because it's 1/2 x, and u of 0 is 0, so we're going to integrate 2 times the integral from 0 to 1 of f of u du. Well, I pointed to the wrong function because I forgot about those bound changes, but notice here's one right here. So the 2 times 6 will be the integral, which is 12. Okay, This one requires a little bit more work. Once you stop the video, think about it. It's going to involve subtracting some of these integrals. Try it, come back and watch my solution. So I'm going to say u equals 2x. So du equals 2 dx. So 1/2 du equals dx. And then I'm going to change my bound. So u of 2 equals 4. U of 1 equals 2. So what I'm integrating is 2 to 4 of f of u du. Now, unfortunately, I'm not seeing a 2 to 4. But I am seeing 0 to 2 and then a 0 to 4 of the same function. So if I think about that rule of integral from a to b of f of x dx is the same as the integral from a to c. Sorry, I'm going to do this a little differently. I know the integral from a to c, two numbers, of f of x dx is the same as the integral from a to b of f of x dx plus the integral from b to c of f of x dx. I'm running out of room. These have to be the same. So what I'm going to do is I'm going to use these two to figure this out. So the integral from 0 to 4 equals the integral from 0 to 2 plus the integral from 2 to 4. And I'm being a little liberal with my notation. This is the one I want. So I'm going to do the integral from 0 to 4 minus the integral from 0 to 2. So negative 8 minus 4 equals negative 12. And then don't I have a 1/2 kicking around here? Yes, I forgot my 1/2. So that times 1/2 will be negative 6. Hope that works for you. Okay, then I got to looking at the next worksheet on Master Math Mentor, and it's about exponentials and logs. We should do those. I didn't give you this handout, so you can just copy down these on the back of another piece of paper, or I just squeezed them on the sheet somewhere. So you've already done something like this in section 4. One thing we didn't really talk about, though, is how can we simplify this to make our work a little easier. 4 times, so what I did is I said this is just 4 times 1 over x, which, because that's a constant, I just slid it in front. Then you got to remember, what's the antiderivative of 1 over x? Well, ln x plus a constant. Notice I need to include the plus c here because these are indefinite integrals. There's no bounds. I'm not going to do any further evaluation. Technically, I should have this in absolute values, signs. However, for this function, I have a 4 times an ln, or 4 times a log. I can bring that number up as an exponent. So another way of writing this is ln of x to the 4th plus c. And because when I raise something to the 4th power, it will always be positive. So I really don't need the absolute value signs. You could have written 4 ln x plus c, or ln x to the 4th plus c. Okay. This one's a similar kind of question. It's not to the 2nd power. This is all to the 1st power, but wouldn't it be nice if this were just a u? So if I say u equals 3 minus 6x, du equals negative 6 dx, because the 3 has a derivative of 0. And then if I divide by negative 1/6, or negative 6, won't that give me this integral to work with? And then because the 4 is a constant, I can slide that out. And I reduced 4 over 6 to 2 over 3. And I'm integrating 1 over u du, which will be negative 2/3 times the natural log of u plus c. And of course, because we're not evaluating, I have to do the back substitution, and I'm running out of room. What if I write it here over here? What if I write this as negative 2 over 3 times the natural log of 3 minus 6x plus c. Notice I probably need the absolute value signs here because I'm not squaring. Well, I could treat this as an exponent where it's squared and then take the cube root, and it's also got a reciprocal going on because of the negative. So I guess we could get by without the absolute values, but we'll leave it that way for this video. So here's another one. It looks suspiciously like another log function. What if I say u equals x squared plus 4, and I say du equals 2x dx? I'm not seeing that extra 2 kicking around, though I am seeing a constant 7. So 1/2 du equals x dx. What that lets me do is that lets me write 7/2 times the integral of x. So I'm doing that substitution, and I'm jumping ahead of myself. See how the x dx is the same as the du? This is the 1/2 du. So I brought the 1/2 out in front. I brought the 7 out in front, and that would lets me replace. That lets me replace that x here. I'm going to erase this. 7 over 2 times the integral of du over u. So the antiderivative of 1 over u is ln u. So I have 7 over 2 times the ln of x squared plus 4 plus c. Why don't I need absolute value signs here? I hope you realize that this will always be a positive number. So I don't need my absolute value signs. And that's a perfectly acceptable answer. Okay, what function has the derivative that's tangent of x? I don't know what that is. So what we're going to do is we're going to do something easier. I'm going to rewrite tangent x into sine x over cosine x. Then what I can do is I can say u equals cosine x. Du equals negative sine x dx. Or negative du equals sine x dx, which lets me replace this with the du and that with u. So negative 1 over u. Du, the antiderivative of 1 over u is ln. And we're going to do that back substitution for the cosine x. Now that's a perfectly acceptable answer. I'm going to ask you a test question that's going to give you this as an answer. Yes, I should have absolute value signs here. How did they go from this to secant? I hope you realize that this is an exponent. I can bring it up. What's the reciprocal of cosine x? Secant x. So do you see how that works? So try that with this cotangent x. This is one of the problems in the FTWK book, so you'll see it. You can skip it when you come to it. But try it right now. Stop the video. Try to do that substitution. What you're going to remember is, in case you're a little stuck, cotangent's the same as cosine x over sine x. So try doing that replacement and the u-substitution and integrating this. So I'm hoping that you were able to do this by yourself. If not, here's what we're going to do. I'm going to write this as cosine x over sine x dx. I'm going to let u be the sine x. So du equals cosine x dx. So that will let me do this substitution, 1 over u du. So it's the natural log of sine x plus c. And because I don't have any kind of squaring going on, I've got to make sure that I leave that in absolute values. Now you should be getting to be old hand at this. What do you think you should be? I'm hoping you think 2 plus sine 2x. So the derivative of that will be 0 plus 2 cosine 2x dx. And of course, I don't have an extra 2 because I'm going to replace this with u. I don't have that extra 2 kicking around. So I'm going to bring it over to the other side. So 1/2 du equals cosine of 2x dx. So 1/2 times the integral of 1 over u du. And notice, right, because I replaced that whole thing with u. This is the 1/2 du. So that's going to become 1/2 times the natural log. And we're gonna use 2 plus sine 2x plus c. Now, just to think back a little bit, will that 2, do I need the absolute value signs? Will this ever be a negative number? Well, this is a sine function that's been shifted up 2, so it'll never dip below the x-axis. The amplitude is 1, so this is minimum values of what? 3 and 1, so this will never be negative. So we could get away with just using parentheses. We don't really need the absolute value signs. So this problem, I'll be honest with you, when I was looking through the handout, I'm thinking, how do we do this? Then I realized that, oh, what if we replace 1 over cosine squared, rewrite it as secant squared, and leave the tan x on the bottom, and then I hope that flags to you that if we let u equals tan x, du equals secant squared x dx, and that lets me just find the integral from 1 over u du. Boy, didn't that get easy looking in a real fast time? So, natural log of the absolute value of tan x plus c. Now, sometimes what we've been doing so far makes it look like, and it says this in the handout, that we should always let u be the denominator. Well, not always. And here's one problem where we wouldn't. If I let u be ln x, and I know du is going to be 1 over x dx, which you kind of got to realize is this is the natural log of x to the 4th times 1 over x times dx. So I can let du equal both of these things, and that gives me this integral of u to the 4th du. Okay, which becomes 1/5 of u to the 5th power plus c. Notice I jumped and did that substitution here. Last example in a very long video. Again, the same kind of thing. We don't necessarily want to have 1 over x squared as u, because we can think of this way, and I'm hoping you realize that the derivative of 1 over x is negative 1 over x squared dx. Remember, this is x to the negative 1. Bring down the negative 1. Subtract 1 from that, which would be negative 2. So then the only thing that we've got extra going on is this negative. So negative integral of e to the u, sorry about that, e to the u du. Because I let this replace that along with moving that negative over in front. So the antiderivative of e to the u is e to the u, so negative e to the 1 over x plus c. And that's some u-substitution notes. Hope you watch it. Jump in and try some textbook work.